Welcome back. Okay, it's time for a mega problem. We're going to find a transfer function. We're going to do a partial fraction expansion to the time domain. We're going to determine the transient and steady state responses. So it's a full problem. It takes everything in the chapter and that I want to cover anyway and puts it all into one problem. All right, it's 5 pages long. It's a big problem. So we're given a bunch of stuff. So make sure you have some nice hot cup of coffee. Well, whatever. I don't want to recommend. Do what you want. You do you. I've got a Diet Coke right here. Caffeine. Got to have the right mental state to do these things. Okay, so there's no initial energy at t equals 0. That's one thing they're telling you. The other thing is the input signal, IG of t, I generator of t, is a sinusoidal cosine 4000 t milliamps. And the response signal, this is a nice problem, is I0 of t. So they're describing the problem and they give you this time domain circuit. So there's a time domain current source which is initially switched out of the circuit, and then it opens at t equals 0. The switch opens and sends the current to the rest of the circuit. It's the same circuit we did in chapter 12 a couple of times. Well, once. 0.72 times, I don't know. So this is a 2 Henry. This is a 10 kilo ohm. This is a 50 nanofarad and ohm. All right, what do they want you to find? They want you to find a bunch of stuff. Okay, it's a good problem. This is like the summary, capstone problem for chapter 13. The transfer function h of s defined as some output signal over some input signal, right? And here it's I sub 0 over I sub g, and I sub g is just the source. I sub 0 is where the heck is I sub 0? I sub 0 is this one here. This is I sub 0, okay? So the transfer function, generally speaking, can be any two signals. So here they've chosen this generator signal, and they've chosen the current through this through the resistor. So that's the first thing they want you to find, is the transfer function defined by these two signals. Then they want you to find the frequency domain signal for this current. Okay, and then C and D, part C and D, they want you to describe the nature of transient and steady state output. And I'll show you what that means. And then E, they want you to do a reverse Laplace transform and take big I of S and turn it back into little I of t, which relates to this transient and SS output. So C, D, and E, parts B, C, D, and E are all kind of together here. So we've got a strategy that I think it'd be good to go over just right here before we actually do it. Otherwise it's confusing as heck. So we're going to do node voltage, and that's going to give it, we'll do that in Laplace domain. So that'll give us I0 over IG. Will give us that. Then we're gonna transform to S domain. Wait, no, we're gonna transform. Sorry, we're gonna transform I of G, or I sub G of T, to I sub G of S. We're going to transform from the input signal, this thing, to the Laplace domain, and we're gonna look at the poles, and that gives us some input into the transient and the SS response. Then we're gonna do a PFE, and we're gonna take IG back to little I of G. We're going to go from frequency domain back to time domain. That's what we're going to do. All right, so let's draw the... so there's a switch in here. There's a sinusoidal signal. This one happens to be a sinusoidal signal, but this will work with any kind of signal. You would just change this. Just change this thing in here. But anyway, there's a signal and then there's a switch. So we can model that in the Laplace domain S I of G, and we'll get rid of the switch, and we're modeling it with U of T, the step function. Okay, this is so we need the time domain, or the frequency domain impedances of this stuff. So Z sub C is 1 over SC. Okay, that's the Laplace domain impedance for a capacitor. So it's 1 over S, 50 times 10 to the minus 9th, 50 nanofarad. That's what it is. And then Z sub L is SL, the Laplace domain impedance for an inductor is just going to be 2S, because it's 2 henries. And so the resistor stays the same. This is still 10 kilo ohms, but this guy, the inductor, it's 2S now, and this cap is 1 over S, 50 times 10 to the minus 9th ohms. This is ohms. All right, we're going to do a node voltage. So this is 0 volts, and up at the top is some voltage V. We don't know what that is, but we're going to use node voltage, so we need a V. So we just throw that in there and hope that it goes away. Really. So we're going to do node voltage, at V, node V, and we're doing it in the Laplace domain. And so in is plus and out is negative. I like to say that all the time because it just sets me up for feeling like I know what I'm doing. But anyway, the node voltage equation is going to be, okay, so we got to guess some current. So this one we'll just go with IG. This is just IG right here. And then we'll guess that there's one coming out of V node, and we'll guess that there's one coming out of V node that way, and we'll guess that there's one coming out of V node that way, whatever V is. So the summing in is positive, so IG is coming in, and then the other three are coming out, so they're all going to be negative. And the first one's V over 10K, and this one's V over 2S, just Ohm's law and frequency domain. And this one here is V over S, V over 1 over. So the over is, cancel and comes up top. The over becomes just right next door. So we got that, and we're trying to get the transfer function I sub 0 over I sub g, but we have I sub g and v, so we don't want v. We want to get rid of v, and it just so happens that Ohm's law at the 10k would gives us an expression for v. V is I0 10k, right? This current right here. This is I0 right here. Yeah, so we can plug this V into here. So plug into the node voltage equation. And what we get is you get I sub, just plug in this V's into this thing here. You get I sub G minus I sub 0. 10,000s cancel, minus I sub 0 10,000 over 2s minus I sub 0 10,000 times 50 times 10 to the minus 9th s. We can, this is I0, we can pull out the, we can factor out the I0s and move all these I terms to the other side and factor out, and you get 1 plus 5,000 s minus 5 times 10 to the minus 4 s. You get that, and then we can solve for I sub 0 over I sub g, our transfer function. It's going to be 1 over all of this stuff, 1 plus 5,000 s. Right? That's what you get. And what we need, we need these standard forms where it's on the bottom, it's s to the n, and then a constant, and then s, and then, you know, we need this descending s thing. It's a rational function, right? A rational function is a polynomial with descending exponent terms. We need to get it into that form. So we have an s and then 1 over s, and if we made this a squared, and then we made this an s, and then we made this a constant. So basically, if we multiply times the reciprocal of this s, so if we multiply times 2000 s over 2000 s, right, then this will become s squared. And that's what we want. We want the first term to not have a constant, right? This guy here, you know, no constant up front. That's the format we want for these things. We always want the highest power of s to not have a constant. That's a rational function. So this thing, some of it's rational function, some of it might just be what we do in circuits. I don't know. But anyway, that's what we want. So we end up with this, which is the format. This is the format we want. And this is h of s, the transfer function h of s. So this is the answer to part A. Okay? And it's in the format we want of descending. The numerator and the denominator are both polynomials with descending exponent values. That's what we want. That was part A. Okay? Part B, we want to know what is I sub 0, right? Yeah, part B. What is I sub 0? So what do we do now? Oh, so I sub 0 of s, just solve the transfer function, or h of s is I0 over I sub g. Solve that for I sub 0, so it's going to be h of s, ig of s. So we have h of s, so it's this stuff with all these s's in it. If we had I sub g, we could get I sub 0 of s, right? So we're given this time domain thing. So I'll rewrite it here. It's 60 cosine 4000 t milliamps. So we can do a direct transform to frequency domain. If you in table 12.1, rule number 6, it says that cosine omega t is s over s squared plus omega squared. So we can go this way. We can go from time domain cosine omega t into this frequency domain. So basically, what we're saying is I sub g of s. We're doing a time domain to a frequency domain. It's going to be, you got to get rid of the units. 60 times 10 to the minus 3. And the cosine omega is 4,000, so it's going to be s over s squared plus 4,000 squared. Yeah, and then plug this. So I sub 0 of s is h of s, I sub g of s. So I sub 0 of s is h of s times, it's h of s times I of g. So h of s times I of g. So h of s is 2,000 s squared plus 2,000 s plus 10 to the 7th. Is this 7? That's h of s. And I sub g we just solved for was 60 times 10 to the minus 3 over s squared plus, and then multiplying the 4,000 squared, it's 16 10 to the 6. This is the second answer of part B. It's the frequency domain, or Laplace domain function for I sub 0, and I sub 0 is our output. It's our output function. It's just chosen as our output function. So now what? Oh, so for part, so this is a perfectly good answer, but not really. If we wanted to go to time domain, we would have to fully factor this. So let's go ahead and do that. Fully factored form. So solve the quadratics. These two quadratics. I don't want to do that because it's just a page of, well, it's just a mess. And anyway, you guys can all solve the quadratics. So if you solve the quadratics, what you get is this stuff times this stuff is just, oops, no, that's okay. So it's 120 s squared, just the numerators multiplied out. And this polynomial right here factors into s plus 1,000 minus j 3,000 and s plus 1,000 plus j 3,000. Those are the h. These come from h. This stuff right here is h, and this stuff over here is ig. So these two factors come from h. And then factoring this polynomial down here, you end up with s plus j 4,000 and s minus j 4,000. Those come, these two polynomials here come from this denominator, which is I sub g's denominator. So the answer to C and D, I don't have a good one, but basically these two roots here, these are the poles of, or they give the poles of h sub s, and these two here give the poles of I sub 0 of s. This, the h of s from the notes, from the chapter outline, there's some stuff in here. This is the chapter outline about the transient response and steady state response. Basically, the poles of h sub s, this gives you the transient response. And it's going to be a damped sinusoid. How do we know that? Because there's about 12 pages of stuff from chapter 12 that tells us that the poles of H sub 0, when they're of this format, will give you the transient response. Now, I don't expect you to, just see that right away. I mean, maybe you can, but they're asking the question this way because this we'll see this stuff later, and this is a good way to look at it. Anyway, this guy here is the steady state. The poles of this guy gives you the steady state response, or it's going to be a steady state sinusoid, and that also comes from chapter 12, right? So basically, the poles of the transfer function h of s determine the transient response, and the poles of I sub g, the input function, which in this case is I of g, or I sub g, will tell you the steady state response. And then you look at the nature of those poles. Like here, it's s plus j4000, s minus j4000. That, it may not be obvious, but that's going to reverse transform into a steady state sinusoid. These poles, it may not be obvious, but these are going to reverse transform into a damped sinusoid when you do Laplace inverse. And then these roots, when you do Laplace inverse, you're going to get a steady state sinusoid. That's the answer for parts C and D, but it's not apparent. In order to really make it apparent, we need to solve for it. We need to do the reverse transform, right? So we're going to do that, and that's part E. We're going to solve for I0 of t, and then you'll see that these roots are what I'm saying they are. So part E, they're asking for what is I0 of t? What is that? So we need to reverse transform big I0 of s. And in order to do that, we need to do a partial fraction expansion. So we're going to do PFE of I sub 0 back to the time domain. This is also known as minus sine L. Okay. So we're going to take this dude right here, this I0 of s. We're going to do a partial fraction expansion and then do an inverse Laplace transform. So it takes up the whole freaking page. So it's 120 s squared. And then there's all these crazy roots. S plus 1,000 minus J 3,000, right? S plus 1,000 plus J 3,000. Those are the roots of H of S, by the way. And then the roots of I of G are S plus J 4,000, S minus J 4,000, right? That's I sub 0 of S. We're going to break that up into a partial fraction expansion. We're going to end up with 4 terms, one for each denominator. So we're going to end up with this plus this plus this plus this. So this is S plus 1,000 minus J 3,000. This one's S plus 1,000 plus J 3,000. This one's S plus J 4,000. This one's S minus J 4,000. And there's going to be 4 constants on the top. It's going to be K1, and another K, and another K, and another K. So this is just partial fraction expansions. It's an algebraic technique that just happens to work with Laplace. So now for physically realizable circuits, that is circuits we can actually build, it turns out that for these kinds of roots, the constants will be conjugates of each other. They'll be complex conjugates of each other. So if we solve for K1, then we know this conjugate, or this constant is the complex conjugate of that. Likewise, these two roots are the constants are going to be complex conjugates. So we only have to solve for K1 and we can get K1 conjugate, and then we can solve for K2 and we'll know K2 conjugate. Okay, so the way these things work, you multiply, like to find K1, you multiply all of this mess through by the denominator, and then you solve it at the pole, right? You solve it at the value that makes the denominator 0. So in effect, what happens when you multiply, like to find K1, when you multiply this denominator all the way through this mess, is these other terms go away, the other K terms go away, and then the denominator in this stuff up here goes away. Look, I'm going to draw a dotted line because it's so K1 is going to be so all of this stuff here minus the denominator K1, or missing the denominator of K1. So it's S plus 1,000 plus J 3,000. The denominator K1 is missing out of this thing here. So, and then but the other three are still there. So it's S plus J 4,000 and S minus J 4,000. And the other three terms goes away, and this thing gets evaluated at the pole. S equals minus 1,000 plus J 3,000, the value that makes this guy 0. So you flip the 1,000, you flip the sign here and you flip the sign there, and that's K1, and so you just plug in this S in here. So this is it's 120 S squared, and S is minus 1,000 plus J 3,000 squared. And then you plug in these stuff here into this S and this S and this S, and then do some math or do some try and simplify it along the way, so you don't have to waste any more trees than are necessary. That was plugging this guy into this thing, you get just J6000. Plugging this S into this guy, you get this stuff. And plugging this S into this guy, you get. I'll make sure I'm. So. Yeah, so this is, so now you can put it in your now I chose to put it in my calculator, and what came out was this thing, 10 to the 3 times 19.2 plus 5.61 J. That's the answer. That's K1. So that's what you do. This is sort of a shorthand way to take a fully factored rational expression, or I'm not sure you call it a rational expression. You take this fully factored partial fraction expansion, that's what it is, and you do a partial fraction expansion. You set up these fractions and you solve for each one kind of like this, and you get an answer. And then it turns out we're going to need the polar form of this. This is rectangular right here, so this is 10 to the minus 3, 20 angle 163.7. It's a constant K, constant. And it's going to be helpful to put this into this exponential, this thing, 20 times 10 to the minus 3 e to the 163.7 degrees. That was K1, right? Then we can solve K2 likewise. It's going to be 120 S squared over the K2 denominator gets crossed out of this stuff. So S plus 1,000 minus J 3,000. And these two roots stay around. So it's S plus 1,000 plus J 3,000. This guy think I have them, or I said we were in minus sign hell. I think these two are switch, but it doesn't matter because the constants are conjugates. But and we evaluate this at s equals j4. Should this be a minus sign right here? No, that's the minus, so I'm eliminating here. I'm really solving for k2 conjugate here, which is fine. I could flip these signs and it's okay. So then you plug in these s values into this stuff, and you get 120 times minus j4000 squared. Just plugging in the s value this value of s into all of these s's, and then trying to simplify along the way. This j4000 in here. This guy comes 1000 plus j1000. And plugging this guy in here, you get s plus 1000 plus j. Wait a minute. Plus j 7000 plus 7000. Wait a minute. Just a second here. Let me. Oh God. Yeah. All right. Then you can plug that into your calculator when you give up playing with expressions. 19.2 minus 14.4j is the answer. And in polar form, that's 10 to the minus 324 angle. So 10 to the minus 3 times 24, or 24 times 10 to the minus 3 if you prefer, minus 36.9, or in exponential form is 24 times 10 to the minus 3 e to the minus 36.9. Okay, we found the k's, and we know that these k's come in conjugate pairs, so we found all 4 k's really. So we plug the k's back into the PFE, back into this guy up here that we first set up. You do that, and guess what you get? So we're going to plug these exponential forms, right? These guys, and their conjugates. We're going to plug them into these k's here. Okay, so that looks like, what does it look like? It looks like, I need to write some stuff up here, but it looks like 20 times 10 to the minus 3 e to the 163.7 over, and that's the first fraction, s plus 1000 minus j 3000. And the second fraction, I'll just write the fractions first, 1000 plus j 3000. This is going to be k conjugate, or 20 times 10 to the minus 3 e to the minus 163.7, just the conjugate. Then the second dude is 24 times 10 to the minus 3 e to the minus 36.9. This constant over here over its fraction, s minus j 4000, its denominator, plus s, this guy, 24 times 10 to the minus 3 e to the conjugate of this, 36.9. Okay, so to get this stuff like frequency sized, we need to use a couple of identities. We got this guy. This guy comes from Euler, e to the j theta plus e to the minus j theta. There's this thing. So if we can get this stuff to look like that, there's that. But before we even get there, we're going to have to use this. Let's see, all of these? Yes, all of these are of this form, the denominators. They're all of s plus a, where a is, it's either this this guy here, or it's the extra real value, right? This guy's just got a imaginary part in it, the A thing. Here the A has a real and an imaginary, but they're all going to be s to the A, and those are all going to, or they're all going to be this 1 over s plus A, and those are all going to transform to e to the minus AT. This is from table 12.1.4. Okay? So, let's see, we did a partial fraction expansion. We solved for the k's and their conjugates. We plugged those k's back into the partial fraction expansion. Now, we just need to do some manipulations so that we can go to time domain. So, if you look at the first two terms, this term and this term, the first two terms of the partial fraction expansion, those, by the way, are from h of s, by the way. BTW, by the way. These first two terms come way back from h of s, and these two terms here come way back from x of, or the output. Is it the output or the input? It's the I sub g. They come from I sub g. It relates to part C and D in the solution. The first two terms are, factor out the numerator, 20 times 10 to the minus third e to the 163.7. And then apply this transform here where 1 over s plus a becomes e to the minus at. And a in this fraction is 1,000 minus j 3,000. That's a. A is 1,000 minus j 3,000. So you get the denominator after the transform becomes e to the minus at, where a is 1,000 minus j 3,000. Okay? That's the first term. The second term here, also factor out the numerator. And then do a inverse Laplace transform on the denominator, where 1 over s plus a is e to the minus at. So you get e to the minus a, where a is 1,000 plus j 3,000. Those are the first two terms. Okay, now we can factor out time, because we're trying to get a time domain expression. And so we need to really get rid of the j's. That's where this identity here comes from, to get rid of the j's. Because we're trying to get a time domain expression that just has time in it. So we can pull the e to the terms of t in there. We can pull those guys out. So we get 20 times 10 to the minus third e to the minus 1,000 t, and that's the same on both of there's an e to the 1,000 t and an e to the 1,000 t, and you're left with the imaginary junk, which is e to the j 3,000 t plus 163.7 plus e to the minus j 3,000 t plus 163.7. Then you can apply this identity right here, where theta is this e to the j theta, where theta is 3,000 t plus 163.7, and you get the half doubles this part. You get 40 times 10 to the minus 3 e to the minus 1,000 t times cosine 3,000 t plus 163.7. Okay, that's C. And then you should see part C, because this is a damped sinusoid, right? There's the damping, and here's the sinusoid. It's a damped sinusoid. That's part C and D. We're asking about the transient and the steady state response. This is the transient response, and it comes from the h of s. Okay, that's the first two terms of the partial fraction expansion. If you take this, you take the last two terms of the partial fraction expansion, which come from IG of S, by the way. That's where they come from. Take these two terms here and do the same thing we did here, or a similar thing that we did here. Factor it, do some factoring, apply this transform, and then apply this identity. And what you get is, you get 24 times 10 to the minus 3 e to the minus 36.9. That's this first term here, this term. And then applying the 1 over s plus a inverse Laplace transform gives you e to the minus at. Applying this to this thing here, where a is minus j4000, you get e to the minus at, where j is minus j4000 t. That was the first, or that was this term. This term over here, similar, you take out the 24 times 10 to the minus 3 and the e to the 36.9. And then you apply the inverse Laplace transform to the denominator, or the whole thing really. The 1 over s plus a, where a is j4000, and you get e to the minus a, where a is j4000 t. And then you can factor out the time portions, and so you end up with 24 times 10 to the minus 3. Wait a minute. Actually, I got partly confused. Over here, on the previous one, we factor out the ones that don't have j in them, but here we don't have any of that form. So we just collect these exponents, and you get e to the j 4000 t minus 36.9 plus e to the minus j 4000 t minus 36.9. Minus sign heck. And then you can apply this identity right here where theta is 4000 t minus 36.9. And so you get 48 times 10 to the minus 3 cosine 4000 t minus 36.9. Okay, that's a regular sinusoid. So see part D, where the steady state is given by a straight sinusoid. So the coolness part, wrap this all up. So I solved this in two pieces here, where the first two terms and then the second two terms, and you just add all that junk together, and you get I0 of t is 40 e to the minus 1000 t cosine 3000 t plus 163.7. That's the this is the transient response, because it's a cosine function underneath an envelope, underneath an exponential decay envelope, and then the steady state response is 48 cosine 4000 t minus 36.9 milliamps. All right, that's I0 of t. That's the answer. Now, I wanted to know what these things look like, so I would draw you a sketch, but I did take the time to plot it. So you have this thing here is the transient, and this guy here is the steady state. So this right here is the transient. See, it starts out at close to 40 because of the phase shift. It's not quite 40, but then it goes up like that, and then it kind of goes down, and eventually it stabilizes and has negligible effect. And then this one is the steady state. That's the 48, which starts at 40 because of the phase shift, right? So there's the steady state and the transient, and if you sum these, if you add these together, you see they're close to zero here at the beginning, and then like at this point, right about here, they're positive, negative, about opposite, which is where the zero is. And if you look, it's a little bit bigger, and then it eventually stabilizes to the 48 amplitude. Okay, so the transient response is very negligible in the circuit. It has very little effect for this particular circuit. Now, that doesn't mean that transient responses are always negligible, but this isn't that bad. And if you think about a complicated circuit, there's a lot of inductive loads, there's a lot of capacitive loads. All of that stuff serves to damp out transients, right? So like back to my house, I have a generator. I flipped it when the power was off. You flip it on, it energizes all the things in my house. And a lot of those, there's a lot of motors that'll just come on, and my air conditioner and whatnot. And all of that serves as a damping. So once again, I'm not trying to dismiss transient responses, but anyway, a lot of math, some good stuff. Do your best to understand these partial fraction expansions. We'll look at some other chapters, and later on in your education, you may come across this stuff in more depth. I remember a class I took where, oh man, it was a whole semester of just doing these partial fraction things. I studied all the time for that class. It was an electrical engineering department, but taught by electrical engineering profs, but it was we didn't look at a single circuit. It was just all math. Anyway, good stuff. Thanks.